Circle segment theorems. We also have several theorems that allow us to find the lengths of all the different segments pertaining to circles. Chords, tangents, secants, radii, diameters, and all their parts formed by intersections are included here. Let us begin. During the next few videos and lessons, we're going to be talking about three major problems. Ones that involved intersecting chords, ones that involve tangents and secants, and ones that involve secant. So I just want to clarify before we begin what we're going to be referring to when we talk about the parts of all of these things. So in the first problem, the intersecting chords. True, there's only two chords here that are drawn. However, when they intersect at a point, they're broken into four parts. So when we refer to the parts of two intersecting chords, we're going to be talking about, say, that part there, and we're going to be talking about this part here, which could be completely different from each other. However, they were the same chord, and now they're two different parts of that chord. And then we have this part over here and this part over here, which again were a part of the same chord. However, at the point of intersection, they were broken into parts. So you can see we really have 1, 2, 3, 4 parts that we're going to refer to in the intersecting chord theorems. Now, when we get to the second problem, a tangent secant problem, a tangent by definition has a starting point and in this case, an ending point on the circle. So it really only touches the circle. If this were to keep on going, it's still a tangent only skims by the circle and touches it at one point. So a tangent is really only going to have one part, right? The tangent. However, this other segment, which is a secant, which say even if it began here and ended here on the other side of the circle, goes through the circle, touches the circle twice. And therefore, there are three different parts that we're going to refer to. The part of the secant, which is outside of the circle, we're going to refer to that as its exterior part. The part of the secant that's inside the circle will be its interior part. But of course, we're also going to be referring to the entire secant. So I'm going to put another line up here just so we could see that, because I do that a lot when I'm doing these problems. If we started here and went all the way to there, right? There, that we have the whole entire secant length, right? So that's the whole entire secant. So again, with a tangent, there's only going to be one part. However, there's kind of three different parts we could refer to when we talk about a secant: the outside part, the exterior, the inside part, the interior, and of course, the whole secant length if it begins and ends at those 2 points. And of course, when we get to a secant problem, it's going to look the same as this secant over here, right? So here you're going to have your interior part. I'll call this interior 1. This over here will be the exterior 1. And then here I'm going to have my interior of the other one. I'll call it my interior 2. This will be my exterior 2. And then, of course, again, we have the whole entire secant, and they do not need to be the same. They could be different, right? So the length of this right here, right there, that's one of the secants, and then the length here is the length of the other one, and they do not need to be the same. They could be completely different. All of those parts could be completely different from one another. So we're going to learn some theorems that are going to help us find some of these lengths. But we're going to begin this lesson with intersecting chords. So here's the first theorem. If two chords intersect in a circle, the product of the lengths of the segments of one chord equal the product of the segments of the other. Now, if you look at this picture, you're going to notice that they draw a circle with intersecting chords. And you're also going to notice that instead of using capital letters here, they used lowercase letters. This is because these lowercase letters here are representing the actual lengths of those parts. Remember, we use capital letters, right, to represent actual points, but lowercase letters could represent actual segments. So this A is really representing this part, and this lowercase b is representing that part, and this lowercase c is representing this part, while this lowercase d is representing that part, right? So this is a really simple theorem. It says that when that happens in any circle, any two chords intersect and create those four parts. If you multiply A and B, which used to be the same chord, and then this other chord came and intersected it and broke it into two parts, that if you multiply A times B, it will always be equal to the multiplication or product of C times D. It's a really cool thing that happens in a circle. Now, there is a proof to this theorem that it will be optional. And in the actual class that I do for this, I'll explain this a little bit more deeply. However, if you want to pause your video and take a look at it and try to understand it, go ahead, do that now. Okay, let's take a look at some problems. So here we go. Part 1, intersecting chords. In the accompanying diagram of a circle, chords A, C, and B, D are drawn and intersect at E. Okay, this looks familiar. Segment DE is equal to 6. I'm going to put that in here. All right. Segment EB is equal to 4. And segment AE is equal to 3. And the question is, find segment EC. Well, since there's no X here, I can put an X here. Now, if we just go back really quickly, see how simple this is. If I multiply A times B, it should always be equal to the product or multiplication of C times D. It's that simple. So when I go back to this problem, and if I use that same idea, that means if I multiply this 3 times the x, I'm going to get 3x. And that will always be equal to the product of the other two parts on the other chord. Will be equal to 6 times 4. That, of course, would give me this very simple equation that 3x is equal to 24. Divide by 3, and my x will be equal to 8. It really is that simple. However, as you are aware, things don't stay that simple all the time, but they're not that much more difficult in these few problems here. But you might look over here at 7-8 and see some representations. Yes, there are problems that lead to quadratic equations, but we've had some practice in that, and we're getting much better at those. Well, let's take a look first at number 2. Again, intersecting chords at point A. They name the circle O. They've given me some representations of the parts formed, so I'm going to draw those in. AE is 12. CE is 8. ED is 6. Find EB. There's no X in this problem, so I'm going to put my own X in what I'm looking for. And again, remember, the two parts of the same chord when multiplied, so 12 times X, should be equal to the other two parts of the other chord it intersects, which is 8 and 6. So right down here, I'm going to say 12 times X, which is 12X, will be equal to 8 times 6. 12x will be equal to 48. Divide by 12, and x will be equal to 4. This is a short answer question, so I'm going to say B is equal to 4 because that was my x. It's as simple as that. Okay, now I'm going to erase these values here because we're using the same circle to do these other problems. So I'm going to erase those, and let's go on to number 7. Number 7 says AE is 3 and EB is 4. CE is x minus 4 and ED is x. Okay, well, just because I have some representations and some binomials doesn't mean I can't just go forward with the very simple theorem that part times part will be equal to the other chord's part times its part. Well, now I do have to remember to distribute this. So I am going to get an x squared minus 4x is equal to 12. Discover that I have a quadratic equation and 3 different families. So I am going to use the method of factoring, which means I'm going to bring all the numbers to the same side. That 12 is going to come to the other side and turn negative and set it equal to 0. And now I'm going to factor this by asking myself, is there a greatest common factor? No. Is this the difference of 2 squares? No. So I'm going to trial and error by opening up 2 sets of parentheses. Remember, we're still equal to 0. So I'm going to have an x here and x here because that's equal to x squared. When the last number is negative, that means my signs are going to be different. And I'm going to come here on my scrap paper. And I'm going to have 1 times 12, 2 times 6, and 3 times 4. I'm looking for a pair that subtract to 4. So 6 and 2. And 6 is larger, which means it's going to share this sign right here. So I'm going to put my negative 6 and my positive 2. And now remember the last step, once we found the 2 binomials that factor that trinomial, I'm going to separate them and set each one equal to 0. X plus 2 is equal to 0. My x minus 6 is equal to 0. And then, of course, x will be equal to negative 2. And x will be equal to positive 6. Now, since one of my segments is represented by x, I know I cannot have a negative answer. So I'm going to reject that. And I'm going to accept this answer right here as 6. And here the question was just find x. So I actually am finished, but I do want to go in here and check my work. So I'm going to just substitute a 6 here, and then 6 minus 4 would make that 2. And as you could see, it works out. The theorem says that these 2 parts, 3 times 4, which are 12, should be equal to the product of these 2 parts, 2 times 6, which is also 12. Now I'm going to get rid of these and do the final question, number 8 over here. So number 8, we have AE, which is 8, EB, which is 9, CE, which is an x plus 2, and then ED, which is an x minus 4. So again, I'm going to set this up as the product of 2 of those parts. This is going to be an x plus 2 times an x minus 4 will be equal to 8 times 9. Now here you have to remember on how to kind of FOIL out this binomial times a binomial. I'm going to get x squared minus 4x plus 2x minus 8 is equal to 72. Then I'm going to Combine those like terms, you get minus 2x minus 8. I'm going to bring that 72 over as well. Minus 72 is equal to 0. Then I'm going to get x squared minus 2x minus 80 is equal to 0. No greatest common factor, it's not the difference of two squares, so I'm going to factor this. I know that this is going to be x and x. I know the signs have to be different because that last number is negative. And then a little tip here, when you're looking for two numbers that multiply to 80 but have a difference of 2, well, I'm going to start kind of in the middle, right? What numbers multiply to 80? An obvious one is 10 and 8, and they have a difference of 2. So it has to be minus 10 and a positive 8, because when you add them, it equals negative 2. When you multiply them, it's negative 80. And again, we don't have to do that last step. We could just jump to the answers here. X is equal to negative 8, because negative 8 plus 8 is equal to 0. And here it's going to be equal to positive 10, because 10 minus 10 is equal to 0. Again, I am going to reject my negative and accept my positive. And there you have it. Now, before we finish, I do want to just introduce one important special case. The special case states that if you have a diameter or a radius, which is half of a diameter, that is perpendicular to a chord, if that's given to you, we can assume that it is also bisecting that chord. That's an important piece of information. And of course, the opposite would also be true. If you saw that a diameter or a radius was bisecting a chord, then you could do the opposite, assume that they are perpendicular and forming right angles. So here in this particular problem, you see that one of the chords, CD, is given to you as a diameter. That means it's just a chord that goes through the center of the circle, right? Cutting it in half. And they're telling us that it's perpendicular to another chord, AB. Well, because we just learned this special case, we know that if it is perpendicular to this chord, it's also bisecting it, meaning those two parts, AE and EB, must be congruent to each other. So therefore, we need less information to do the same problems that we've been doing. For example, if they tell us that AB, that whole chord, is 8, we know that it's been bisected because it's perpendicular, and therefore we can put a 4 and a 4 here. And then they tell us that CE is 8, and we're looking for this little part right here. Well, it's not that difficult. If we go back to our original theorem that says part times part is equal to part times part, which means 8x is equal to 16. And I'm going off the bottom of the page, which means x would be equal to 2, which means ED would be equal to 2. And I'm just going to do one more of these. You could try the other ones yourself, and we'll go over those in the class. I'm going to erase this since we're using the same picture. And we'll do, say, number 10. Well, if AB is 16, well, because they give us that it's perpendicular, we know it's cut into two equal parts, which means we can assume that each one is 8. And if CE is 16, find ED. So once again, 16 times its other part, which is x, will be equal to 8 times 8. 16x is equal to 64. Divide by 16, and x is equal to 4, or ED is equal to 4. And there you have it, the intersecting chords of a circle. I hope you found this video useful, and if you have, please subscribe to my YouTube channel. See you later.